So in this problem, we're going to be calculating the spring constant of the entire wire. Now, problem 1 states, what's the spring stiffness of the entire wire, considered as a single macroscopic or large-scale, very stiff string? Now, if you take a look at it, we can use Hooke's law. Hooke's law. Now, Hooke's law states that force equals negative kx. But in this context, we can do it as k delta L because length is changing in this problem. Now, some of you may be asking, "Oh, Professor Lohmeyer, you forgot the negative in front." Well, we don't do that, and the reason for that is because it's a magnitude. We're calculating a magnitude only. It's not a direction vector, so that's why we don't use the negative sign. So, this law tells us that force needed to extend or compress a spring by a distance delta L is proportional to that distance. So, let's calculate it. Now, given the mass of M is 234 kilograms, it's attached to a wire, we know that the force applied to the wire is due to gravity, which we can also calculate with an equation of F equals mg, with g representing, obviously, g equaling 9.81 meters per second squared, the constant. And the extension delta L caused by this force, delta L, is 1.22 centimeters. But remember, we want to keep it in SI units, standard physics units. So we're going to convert it to meters. So that's going to be 0.0122 meters. Now, applying these values of Hooke's law and rearranging to solve for k, let's do that. So, basic algebra. So if F equals k delta L, we want to isolate k. I'm going to divide it by that bitch. And we're going to get k equals F delta L. Alrighty. Now let's plug this some bitch in. Alright, so k equals, now we know force can be the same thing as mg. So mass is 234. Kilograms is already an SI unit, so we don't have to convert that to anything else. And 9.81 meters per second, that's also an SI unit, so just leave it as that. Divided by 0.0122. And when we calculate that, we get, one second, we get 188,159 newtons per meter. So that is how you solve question 1. Now let's delete this motherfucker. Alright. For question 2 states, how many side-by-side atomic change, long springs, are there in this wire? This is the same as the number of atoms on the bottom surface of the iron wire. Note that cross-sectional area of one iron atom is 2.28 times 10 to the negative 10th squared, meters squared. Number of side-by-side long chains of atom is, so basically, they're literally just asking you to understand, to determine the number of atomic change, that is. Now, to understand the atomic structure of the wire, we have to calculate the number of atomic chains in the wire's cross-section. So these chains are essentially columns of atoms that run the length of the wire. And knowing the number of these chains will later help us calculate the stiffness of the single atom bond. So the cross-sectional area of the wire, we're going to name that A sub wire. And it's the square root of its side length. So A sub wire, that's going to be 0.15 centimeters. Now remember, let's convert that to meters. It's going to be 0.015 meters. Hold on, that's not right. Excuse me. 0.015 meters. Yeah, meters. So we convert this measurement to meters, which also, remember, because it's square of its side length, we square the son bitch. 0.015 squared, and we calculate the area. So the area of a single atom modeled as a square with the interatomic distance, d, as the side length is d squared. And d squared is, according to what they gave us in the given value, is 2.28 times 10 to the negative 10th meters. Now we determine the number of these atomic squares that can fit into the cross-sectional area of the wire. If you see the photo, it shows just that. So this is the total number of atomic chains. And we're going to name that n, which we find by dividing the wire's cross-sectional area by the number of atomic squares. So to put it visually, that's just going to look a wire divided by d squared. Right, now let's do that. So that's going to be 0.0015 squared divided by 2.28 times 10 to the negative 10th. So 0.0015 squared divided by 2.28 times 10 to the negative 10th. I forgot to put a square on that. Sorry about that. Squared. And you're going to get 4.33 times 10 to the 13th, which is n. So in this problem, the number of atomic chains is 4.33 times 10 to the negative 10 to the 13th, numbers. So that's a lot. Now, let's move on to part 3. Now, part 3 isn't that hard, actually. So they're telling us how many interatomic bonds are there in one atomic chain running the length of the wire. So they're asking for a number of bonds in total length again, similarly. So we're going to compute the number of bonds in one chain. Jesus. Now each atomic chain is composed of atoms connected by interatomic bonds. So, like in chemistry. It's like a guy with a bunch of glasses. It's like if a spider had glasses, kind of thing. ... So, to find the total number of bonds, we're going to name that n again, just this time a little n. In a chain, we divide the length of the wire by interatomic distance. So since the length of the wire they gave us is L equals 2.4 meters, now that's already in SI units, you don't have to convert that. And each atom is separated by the interatomic distance d. So the total number of bonds in one chain, now that equation is going to be n equals L over d. L is the length of the wire, and d is the interatomic distance. Now, they already gave us that value. So, that's going to be 2.4. 2.4 divided by 2.28 times 10 to the negative 10. 2.28, now let's calculate that. Now we're going to get 1.05 times 10 to the 10th. No units because it's just a number. Number 3 answer. Right, now let's move on to number 4, final number. Right, so number 4 states, what is the stiffness of a single interatomic spring? Well, quote-unquote spring, whatever the fuck that means. Now, this might be a little harder to conceptualize than usual, but finally, we're ready to find the stiffness. We're going to name that Ks initial of a single interatomic bond. The overall stiffness, we're going to name that Ks, of the wire's combined effect of all these tiny springs, the interatomic bonds, and they work in parallels. So to isolate the stiffness of one out of all of them, we consider how the overall stiffness relates to a single bond within the chain and across all the chains. So what do we use? Well, we can use the similar formula of Ks sub I. Actually, it's not similar. It's a little new, but it's Ks sub I of Ks times N over big N. So we use this to find the stiffness of a single bond by multiplying the overall spring constant by the number of bonds in one chain, and then we divide the total number of chains from that. So substituting in the previous value, we determine that, now let me see, oh geez, what was the previous value? I believe it was K of S. Where is it? K of S, where are you? Where are you? It's the first answer. Sorry about that. So the first answer is 188,159. And we're going to multiply that by the little n that we just calculated, 1.05 times 10 to the 10th. And we're going to divide that by all the n's that we calculated in problem 2, 4.33 times 10 to the 13th. Now let's calculate that. 188,159 times 1.05 times 10 to the 10th divided by 4.33 times 10 to the 15th. The final answer that we get is 45.63 Newton meters. I believe that is the final answer. Let me check. Yeah, seems like it. 45.63, math checks out. All right. Now, there's a chance that my math could be wrong. I haven't done classical mechanics in a long time, but I hope this helps, and I believe this is the right answer, so I love you, babe. Bye.